The Bloom Filter Registry is a probabilistic data structure management system designed for memory-efficient set membership testing across distributed nodes. The system maintains a collection of independent filter instances, each initialized with a fixed bit array of size m and k independent hash functions. Filters operate in append-only mode once constructed. The registry tracks filter metadata including creation timestamps, hash function seeds, and collision statistics. Registry instantiation requires specification of expected element count n, desired false positive probability p, and the number of hash functions k. The system calculates optimal bit array size m using the formula m equals -n times log base 2 of p squared divided by natural log of 2. Default false positive probability is set to 0.01 if not explicitly provided. Once initialized, filter parameters become immutable. The add operation inserts a new element into a specified filter instance within the registry. The operation applies all k hash functions to the input element, generating k bit positions within the range 0 to m-1. Each corresponding bit in the filter array is set to 1. Multiple elements may hash to overlapping bit positions. The operation completes in constant time relative to element size. The query operation tests membership of an element against a specified filter. The system applies the same k-hash functions to the input element, retrieving k-bit positions. If all k-bits are set to 1, the system returns a positive result. If any bit is 0, the element is definitely not in the set. Positive results indicate possible membership with probability bounded by p. Registry filters do not support element deletion. Attempting to remove elements requires maintenance operations involving filter reconstruction with updated element sets. The system provides a compact method that rebuilds filter state from a snapshot of known elements. This operation is blocking and should be scheduled during off-peak periods. Compaction preserves all metadata except internal timestamp records. Hash function selection impacts filter performance and collision distribution. The registry supports seeded cryptographic hash functions, including SHA-256 variants and murmur hash with configurable seed values. Seeds are derived from filter creation timestamp and instance index. Collision rates increase as element count approaches the theoretical saturation point. Monitoring tools track bit occupancy ratios to detect degradation. The registry maintains separate instances for different logical domains within distributed systems. Each instance receives its own namespace identifier and metadata container. Instances do not share bit arrays or hash function seeds. Cross-instance queries require explicit instance selection. The system prevents accidental mixing of incompatible filter parameters through type enforcement at the API boundary. Serialization of filter state produces a compact byte representation of the bit array paired with metadata headers. The format includes protocol version identifier, bit array size, hash function identifiers, and creation epoch timestamp. Deserialization validates header checksums before reconstructing internal structures. The system rejects corrupted filters with explicit error codes rather than failing silently. Distributed registry synchronization uses eventual consistency semantics. Peer nodes gossip filter state updates at configurable intervals. Conflicts in filter additions are resolved by union operations, preserving all previously observed elements. The system guarantees that additions eventually propagate to all replicas given sufficient time and network connectivity. Temporal ordering is maintained through logical vector clocks. Memory consumption for each filter instance is approximately m bits plus overhead for metadata structures. The bit array occupies m bits divided by 8 bytes. Overhead typically comprises 256 bytes for hash, function seeds, and configuration parameters. Scaling filters to billions of elements requires careful sizing of m to maintain acceptable memory footprints. Bit array allocation uses aligned memory blocks to optimize cache behavior. The registry exposes monitoring endpoints that report per filter statistics including total elements added, query throughput and requests per second, and measured false positive rates. False positive rate estimation uses random sampling of known elements. The system tracks bit occupancy as the count of set bits divided by m. High occupancy correlates with increased false positive probability and indicates potential filter saturation. Error handling in the registry follows standardized codes and messages. Queries against non-existent filters return error code 404 with descriptive text indicating the missing instance. Attempts to add elements to finalized filters return code 409 indicating state conflict. Invalid element types return code 422 with schema violation details. All errors include request identifiers for correlation with server logs. Backup and recovery procedures preserve filter state through periodic snapshots written to durable storage. Snapshots include complete bit arrays and metadata. Recovery from snapshot is deterministic and does not depend on element order. The system supports incremental snapshots that only store changed bits since the previous snapshot. Restoration time scales linearly with snapshot size and I/O bandwidth. Configuration parameters for the registry system include the default hash function type, gossip interval in milliseconds, snapshot frequency in hours, and maximum concurrent instances. The gossip interval defaults to 5000 milliseconds. Snapshot frequency defaults to 24 hours. Maximum concurrent instances defaults to 10,000. These values are configurable at startup through environment variables or configuration files. Integration with external systems requires filter state export in JSON or binary formats. The JSON export includes human-readable metadata and base 64 encoded bit arrays. Binary export produces raw bytes suitable for transmission and storage. Both formats include version identifiers enabling forward compatibility. Importers validate format headers before processing to prevent accidental misinterpretation of data. This concludes the technical reference for the Bloom Filter Registry system. Administrators should consult operational logs for filter performance trending and schedule maintenance compaction when bit occupancy exceeds 80%. Load testing recommendations suggest 10 million element operations before production deployment. Contact the technical support team for clarification on protocol specifics or advanced configuration scenarios.